For as long as we've looked up at the night sky, we've wondered if we're alone. The universe is vast, billions of galaxies, each holding billions of stars, and around many of those stars, planets. Worlds that could look like ours, feel like ours, maybe even live like ours. And yet, in all our searching, we've heard nothing. No signals, no messages, no alien footprints in the cosmic sand. Our telescopes see endless suns. Our probes travel further each year, and still silence. It doesn't make sense. Statistically, life should be everywhere. There should be civilizations far older and far more advanced than us. But if that's true, where are they? Maybe we're missing something. Maybe they've been here and we just don't recognize the signs. Or perhaps, and this is the most chilling possibility, we really are alone. Leave a like and subscribe to the channel, as tonight we explore one of the greatest mysteries in science. Why, in a universe that should be full of life, we have found none. Is life easy to start and common everywhere? Or is it very rare? Here are some ideas about aliens and life beyond Earth. Extraterrestrial life exists. This idea says that life exists somewhere else in the universe, maybe even in our own solar system. Tiny living things might be on Mars or on some moons around Jupiter and Saturn. Smarter life forms, like advanced civilizations, might live on planets going around other stars. The Fermi Paradox. The Fermi Paradox asks, if smart life is common in the universe, why haven't we found any proof of it? Some think smart civilizations destroy themselves. Others say they're too far away or don't want to talk to us. Ancient aliens. This idea suggests aliens came to Earth long ago and changed human history and culture. Supporters point to old artwork and writings as proof that aliens visited us. UFO sightings. People often say UFOs prove aliens visit Earth. Many sightings can be explained by natural events or human-made objects, but some can't be explained and might be evidence of alien visits. The simulation theory. This theory says our whole reality is a computer program made by an advanced civilization. While not exactly about aliens, it suggests the creators of this simulation could be aliens. Let's start with the basic question. Do aliens exist? According to the Drake equation, created in 1961 by astronomer Frank Drake, there's a good chance smart life exists elsewhere in the universe. The equation looks at things like how many stars are in our galaxy, how many planets could support life, and the chances of life starting on those planets. Using these factors, the Drake equation says there could be millions of smart civilizations just in our galaxy. But the question is, have we ever met these civilizations? Many people think we have, and there are countless stories of alien sightings, kidnappings, and meetings. However, there's little solid proof to back up these claims. What might aliens look like? The common picture of aliens as small, green creatures with big eyes comes from movies and TV. However, aliens probably wouldn't look like this at all. In fact, we can't predict what aliens would look like because their appearance would depend on their planet's conditions. For example, if aliens evolved on a planet with strong gravity, they might have shorter, stronger bodies. If they evolved on a planet with harsh radiation, they might be better at handling radiation. Some alien species might not even have bodies like we know them. They might be pure energy or exist as a group mind. Why would aliens visit Earth? There are a few possible reasons. Some scientists think aliens might be interested in our planet because of where it sits in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to grow. Aliens might want to study our planet to learn how life survives in these conditions. Another reason aliens might visit Earth is to contact us. If there are millions of smart civilizations in the galaxy, some might be trying to talk to us. However, if this is true, they might be communicating in ways we can't understand. Their communication methods might be very different from ours. If we make contact with aliens, it could deeply affect how we understand the universe. It could challenge what we believe about our place in space and make us face big questions about life, the universe, and everything. Now let's think about the Fermi paradox. This puzzle asks, if there are so many smart civilizations out there, why haven't we seen proof of them? Why haven't we picked up signals or seen spaceships from other worlds? One possibility is that advanced civilizations destroy themselves. With technology comes the power for destruction, whether through environmental damage, war, or other disasters. Many smart civilizations might reach a point where they can't survive and eventually fail. Another possibility is that smart civilizations don't want to contact us. Maybe they're not interested in Earth or talking to other species. Or maybe they're too far away to detect our signals, and we're too basic to detect theirs. Whatever the reasons, the Fermi paradox stays a mystery and causes much discussion. Let's look at the chance of life in our own solar system. While we haven't found smart life, there are promising signs that tiny life might exist on other planets or moons. NASA's Mars rover has found methane on the planet's surface, which could be a sign of tiny life. Scientists have also found evidence of underground oceans on some moons of Jupiter and Saturn, which could support life. If we find evidence of tiny life in our solar system, it would be a huge discovery and could greatly affect how we understand life in the universe. Let's think about what finding smart life would mean. If we contacted an alien civilization, it could deeply impact our society and how we understand the universe. For one, it could challenge what we currently believe. We might need to rethink our ideas about our place in space, our religious and philosophical beliefs, and how we understand where life comes from. It could also raise questions about the right way to interact with other smart species and what responsibilities come with such interactions. Another potential impact is on our technology and scientific progress. If we met a more advanced civilization, we could learn from their technology and knowledge, possibly speeding up our own progress. On the other hand, it could also be dangerous if the aliens want to harm us. It's hard to say for sure whether aliens, if they exist, would be dangerous to us. We have no solid proof of smart alien life, so any guessing about their intentions or behaviors is just a guess. Some people argue that aliens could be dangerous if they're more technologically advanced than us and can conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely understand the universe better and might be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply watching us from far away without wanting to interact at all. Overall, while it's fun to guess about the potential dangers of alien life, the truth is we don't know enough to make any final conclusions about their intentions or behaviors. The search for alien life should be done with an open mind and healthy curiosity, not fear or worry. Regardless of potential impacts, the search for smart life continues. We're constantly developing new technology and improving our methods to search for signals and evidence of other civilizations. While the chances of finding smart life may be small, the pursuit of knowledge and discovery is valuable on its own. Venus is nearly the same size as Earth, making it one of our closest neighbors in the solar system. With an average radius of about 3,760 miles, 6,052 kilometers, it's about 95% the size of Earth. Its mass is about 81.5% of Earth's. This similarity in mass and size means Venus also has a density close to Earth's, about 5.24 grams per cubic centimeter, suggesting a similar rock-iron makeup. Venus and Earth have similar structures. a central iron core surrounded by a rocky mantle and a thin crust. Venus's core, while not as well understood as Earth's, is thought to be partly liquid, like Earth's. This iron core is estimated to be about 2,000 miles, 3,200 kilometers, across. Above the core sits Venus's mantle, made of rock that extends up to about 1,550 miles from the planet's center. This is covered by a thin crust thought to be 6 to 12 miles thick. The rotation of Venus is unique among planets in our solar system. Unlike most planets that spin in the same direction they orbit the Sun, Venus rotates in the opposite direction. Scientists don't fully understand why, but some think it might be because of a huge collision with another object in the past that changed how the planet rotates. Venus rotates very slowly. A full rotation on its axis takes 243 Earth days, the slowest rotation of any planet. This slow rotation contributes to the planet's lack of a strong magnetic field. Another odd thing about Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its rotation period. Because of its backward rotation and orbit around the Sun, the solar day on Venus is about 116.75 Earth days. The planet's year, the time to orbit the Sun, is about 225 Earth days, which is shorter than its rotation period. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of Earth's surface gravity. This means if you could stand on Venus, you'd feel slightly lighter than on Earth. However, the extreme air pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be relatively young, with a fairly low number of craters, suggesting a surface age between 300 million and 600 million years old. Scientists think Venus goes through a cycle where heat from inside causes the surface to be repaved in a global event. There's strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes at its surface, ranging from less than a mile across to over 150 miles, 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no clear proof that these volcanoes are still active, though recent studies suggest some may have erupted within the last few million years. Despite apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus has mountain ranges and valleys similar to those seen in active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our planet. This might be because of the planet's slow rotation, which limits the effect needed to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and interesting features. The atmosphere is mostly carbon dioxide, 96.5%, with most of the rest being nitrogen. However, there are also traces of other gases like sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This makeup is very different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere, extending from the surface to about 40 miles up, the mesosphere, stretching from the top of the troposphere to about 56 miles high, and the thermosphere, which reaches up to 125 miles above the surface. Above this is a transition region called the exosphere that merges with space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 867 degrees Fahrenheit, 464 degrees Celsius, hot enough to melt lead. There's very little temperature difference between day and night or between the equator and poles because the thick atmosphere distributes heat efficiently. This results in a nearly constant furnace-like temperature all over the planet's surface. The air pressure on Venus is enormous, about 92 times greater than Earth's at sea level. This equals the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, about 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is always covered in thick clouds that blanket the entire planet. These clouds reflect about 75% of sunlight that reaches Venus back into space, which is why Venus is so bright and easy to see from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in something called superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus has the highest mountain in the solar system, Maxwell Montes, rising 20 kilometers, about 12 miles, above Venus's average surface level. The planet's surface is also marked by many impact craters, extensive lava flows, and unique features like coronae, circular structures caused by hot material rising from the mantle, and arachnoids, circular structures with complex patterns of cracks. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant earthquakes like Earth. However, recent studies suggest Venus may still be geologically active. Venus has been a target of interest since space exploration began. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all helped us understand the planet better. The Venera program achieved many firsts, including the first human-made device to enter another planet's atmosphere and the first successful landing on another planet. These missions gave us valuable data about Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to see through the thick clouds. This mission showed details about Venus's surface features and geology. Despite the challenges from Venus's harsh conditions, scientists are interested in exploring the planet more. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geological history and air conditions, providing insights into whether Venus might have once had liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an interesting world of extremes. Its harsh environment creates big challenges for exploration, yet its similarity to Earth in size and makeup, along with hints of possible past water and geological activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the edge of major discoveries that could change how we understand the solar system and our place in it. As a mirror of our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Space has always captured humanity's imagination. Among all the objects in the sky that have fascinated us, Jupiter stands out as the largest planet in our solar system. Its bright stripes and famous Great Red Spot make it easy to recognize. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown greatly with advances in space technology and exploration. Jupiter is a gas giant made mostly of hydrogen and helium. Its diameter is about 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen inside its outer core. Jupiter's famous bands are actually high-pressure zones with lighter-colored clouds. Its darker regions are low-pressure zones. The bright colors we see come from different types of clouds. Ammonia crystals create the white bands, while other chemicals produce reddish, brownish, and yellowish colors. The Great Red Spot is Jupiter's most recognizable feature, a lasting high-pressure region in the atmosphere that creates a storm that's been going for at least 300 years. The Great Red Spot is the biggest storm on Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times Earth's diameter, though its size changes over time. Notably, it has been getting smaller in recent decades. The storm has been watched continuously since the late 1800s, but historical records suggest it existed for at least 300 years. The Great Red Spot sits in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still being researched. Scientists think the color may come from complex organic molecules, red phosphorus, or possibly sulfur compounds. The exact chemical reactions that give the spot its bright color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, showing the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is puzzling. While storms on Earth last days or weeks at most, the Great Red Spot has lasted for centuries. This is likely because of Jupiter's fast rotation and lack of a solid surface, which reduces friction that would slow down the storm's energy. The Great Red Spot gives us a window into Jupiter's atmospheric behavior, a gas giant with conditions very different from our home planet. Understanding this huge storm not only reveals Jupiter's secrets, but also sheds light on broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world of its own. Io is the most volcanically active body in the solar system. Its surface is covered in sulfur and sulfur dioxide, giving it a colorful, spotted appearance. Europa has a crust of ice, and scientists think it might have an underground ocean, making it a potential place for alien life. Ganymede, the largest moon in the solar system, is the only moon known to have its own magnetic field. Callisto, marked by an extremely cratered surface, is thought to have an ocean beneath its surface as well. As of early 2025, Jupiter was known to have 79 moons, but more may have been discovered since then. Saturn isn't the only planet with rings. Though much fainter and smaller, Jupiter also has rings made mainly of dust particles from impacts on the planet's small inner moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, including Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its makeup, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made important discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and its probe made a direct dive into Jupiter's atmosphere, providing the first direct measurements of its makeup. The Juno mission, still ongoing as of 2021, has made important contributions to our understanding of Jupiter's internal structure, atmosphere, and magnetic sphere. Jupiter, the huge gas giant, remains a focus of curiosity for astronomers and space fans alike. Its impressive size, complex atmospheric behavior, many moons, and faint ring system make it a fascinating object to study. As we continue to explore Jupiter through telescopes and space missions, we uncover the secrets it holds, enriching our understanding of the universe. For now, we marvel at the show Jupiter conducts, its presence a testament to the complex, diverse, and vast nature of our solar system. We live in a galaxy called the Milky Way, which contains hundreds of billions of stars. How did we get here, and what is our future? These questions involve galaxies in every way. The known universe contains 200 billion galaxies, each unique, huge, and active. Where do galaxies come from? How do they work? What is their future, and how will they die? This is the Milky Way, our galaxy about 12 billion years old. The galaxy is a huge disk with enormous spiral arms and a central core. It's just one of countless galaxies in the universe. Galaxies are massive collections of stars. First and foremost, a typical galaxy could contain 100 billion stars. They're actually star nurseries, the places where stars are born and die. Stars in a galaxy form in nebulae, which are concentrations of dust and gas. Our galaxy contains billions of stars, many with planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we thought the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble changed everything. Hubble observed the universe using the most advanced telescope available at the time, the 100-inch Hooker telescope on Mount Wilson near Los Angeles. Far, far away, he saw fuzzy masses of light in the darkness. He realized they weren't individual stars. They were entire cities filled with stars, galaxies far beyond the Milky Way. Astronomers received an existential shock. We went from thinking the Milky Way was the only galaxy in the universe to knowing there are billions of galaxies, all in a single year. Hubble made one of the greatest discoveries in astronomy when he found that the universe contains a huge number of galaxies rather than just one. Galaxies are huge on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years, the distance light can travel in a year. Our galaxy's diameter is over 100,000 light-years, and we're now 25,000 light-years from its center. However, in the big picture, even our galaxy seems like a tiny dot. While the Milky Way seems huge from Earth, when compared to other galaxies, it's actually quite small. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our cosmic neighborhood and much bigger than Andromeda. But M87 is tiny compared to IC 1101, which is 6 million light-years across, the biggest galaxy ever found. It's 60 times the size of our Milky Way. It's common knowledge that galaxies are huge and everywhere. But why? The origin of galaxies is a key mystery in space science. About 13.7 billion years ago, the universe began with what we call the Big Bang, a period of intense heat and density. We know there couldn't have been anything like a galaxy at that time, so galaxies must have come from that very early universe and formed from it. For stars to form and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to appear only 200 million years later. The earliest galaxies formed as their masses began to cluster together because of gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Many galaxies are visible to Hubble. The light we see from distant galaxies now actually left those objects many millions or even billions of years ago. What we see now is the distant past of those galaxies because it took so long for their light to reach us. The Hubble Deep Field shows a collection of fuzzy dots. They're quite different from the galaxies we see now. We can barely make out these little specks of light. Those fuzzy patches of light are actually millions or billions of stars beginning to combine. The oldest galaxies are shown by these barely visible spots. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second type of telescope, one too large to send into space, is needed if we want to travel much farther back in time. Not only can newer telescopes identify early galaxies, but they can also trace their evolution. The evolution of galaxy and galaxy cluster formation can be followed. All the galaxies that have developed since the universe was just a few 100,000 years old are leaving their marks for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and astronomers are watching this process. As far as we can tell, the largest structures in the universe today started as star clusters that evolved into galaxies, formed clusters of galaxies, and ultimately came together into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in early galaxies. However, modern galaxies look organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the answer. Galaxies are shaped by gravity, and its effects determine their fate. At the center of most galaxies sits an incredibly strong and destructive gravity source, and our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These star collections may take many forms, from spirals to giant spheres of stars. As far as we can tell, however, there's still a lot we don't understand about galaxies. How did galaxies evolve into their current forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They're messy and chaotic. They begin as chaotic formations, then over billions of years develop into more orderly forms like the Whirlpool Galaxy. The Milky Way wasn't born from a single galaxy but from a cluster of several. Our Milky Way started as a collection of different formations, objects of various sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the different parts together. Over time, it gradually draws stars closer. They speed up and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process happened countless times throughout the universe. While visually different, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers wondered what could possibly change a galaxy's behavior. They found out a black hole. Not just any black hole, but a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first sign of supermassive black holes. Black holes in these galaxies are eating their surroundings like a giant feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes eat their food so fast that they shoot it out into space as beams of pure energy. They call it a quasar. The presence of a quasar indicates a supermassive black hole at the center of the galaxy. But what about the Milky Way? There's no quasar here. Does it rule out a supermassive black hole? Watching the motion of stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like planets that circle the sun, stars also move because of gravity. What we discovered was a strange and violent environment at the center of our galaxy. Everything is more extreme. Things move very quickly. Stars pass one another at high speeds. It's unlike any other place in the universe. The photos of stars in orbit showed a remarkable phenomenon. They had to be traveling at 1 million miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This movement was the clear evidence for a supermassive black hole at the heart of our galaxy, as it's the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So is there any danger to Earth? We're in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole at the heart of the Milky Way is 25,000 light-years, many trillions of miles. For now, Earth is safe. Although supermassive black holes are the source of huge amounts of gravity, they're not strong enough to hold galaxies together. In reality, the rules of physics say galaxies should speed away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered: dark matter. And it's everywhere. Supermassive black holes found by astronomers sit in the centers of galaxies and cause stars nearby to move rapidly. However, they're not enough to hold together all the stars in a vast galaxy. So what does hold them together? It was a mystery until a bold scientist suggested that something unknown was at work. Fritz Zwicky, a Swiss astronomer, wondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity wasn't enough. Therefore, he figured out it must be something that had never been discovered before, something that had never even been considered. He called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he irritated the astronomy community. But this was a brilliant idea, and he was right. It's possible that individual galaxies are also held together by the mysterious substance Zwicky called dark matter. Galaxies depend on dark matter as a kind of protective framework that keeps them from collapsing and moving around. Now scientists have discovered that dark matter does more than just hold galaxies together. It may have also started their formation. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into galaxies' cores. However, the nature of dark matter is still a mystery to physicists. Strange things happen with dark matter because we don't know what it is. Obviously, it's not made from the same stuff humans are. You can't push against it. You can't feel it. However, it's likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be plentiful across space. That means there must be at least 6 times as much dark matter as regular matter, the stuff humans are made of, in the universe. And the way the universe seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space through a process called gravitational lensing. It warps light. The existence of dark matter can be tested using gravitational lensing. As a ray of light from a distant galaxy travels toward us, its path will be bent around a huge collection of dark matter because of its greater gravitational pull. Some distant galaxies indeed seem stretched and warped when seen through the Hubble telescope. The picture distortion is due to the presence of dark matter. We can figure out the density of dark matter by carefully examining the shapes and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the universe is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and can't be detected, dark matter rules space. These galaxies seem to be completely alone. It's true they're trillions of miles apart, but actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters containing tens of thousands of galaxies. The Milky Way's place in the universe remains interesting. If you look at the big picture, you'll see that our galaxy is part of a smaller group of galaxies with about 30 members total. Our galaxy and Andromeda are the two largest members of this group. Further observation shows, however, that our galaxy sits inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand space. Galaxies are the huge star empires. The shapes range from enormous balls to complex spirals. The problem is they're always changing. When we stare out into space, it's easy to assume our galaxy hasn't changed in ages. It has. The Milky Way is an active galaxy. Over billions of years, its basic nature has been changing. Galaxies don't only change, they move as well. And sometimes they run into each other. The two galaxies will merge over millions of years when they collide. This kind of collision happens all the time in space. Our own Milky Way is no exception. We're on a collision course with the galaxy Andromeda, and that's bad news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy rushing toward us at a huge rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and throws them into empty space. As we approach doomsday for the Milky Way galaxy, it would be amazing to watch. The two galaxies will eventually pass through one another and merge into a single one. The Milky Way and Andromeda as we know them will stop existing, and a new galaxy called Milkomeda will be born. It will look like a completely new galaxy. There's no escaping what's going to happen. The question is, what does it mean for planet Earth? We might either be thrown out into space when the arms of the Milky Way galaxy are torn apart, or we could end up in the middle of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide, but this age of galaxies eating each other will eventually pass. Because there's an even more destructive force in the universe. A force that nothing can stop. It will eventually tear the universe apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which controls the universe, is much more mysterious. We don't have the slightest idea why it's there or what it's made from. We don't really know. We know it's present, but beyond that, our understanding is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contains tiny springs. In the far future, scientists predict that dark energy will win over dark matter in the universe. And with that victory, galaxies will finally begin to drift apart. Galaxies will eventually die off because of dark energy. It will do this by speeding up the expansion of the universe, forcing all galaxies to move farther and farther away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the universe will disappear before our eyes. The rest of the universe won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this won't happen for an extremely long time. The universe is doing well right now, and galaxies are creating good conditions for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason life has evolved on Earth is because our tiny solar system formed in the right part of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy might be extremely dangerous. In point of fact, the closeness of our solar system to the core of our galaxy would make it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We're therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone where conditions are just right for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The universe is very large, and the really incredible part is that we continue to learn new things about it. Every time we think we've figured out a solution to a problem, we discover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are full of mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomy community would accept the existence of dark matter and dark energy? We should be amazed to be alive at this particular moment in cosmic history, on this particular planet, on the edges of this particular galaxy, with the ability to think about questions and seek answers across the whole universe. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a lucky home for smart life. Our fate is connected with that of every galaxy. Ultimately, our fate rests in their hands because they're the ones who created us and are shaping who we are. We used to only know about the planets that circled around our sun, but now we know there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very violent. Planets are made the same way everywhere. They come from the dust and other things left over after stars are born. So if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know they're just a small part of the huge family of planets in the sky. It's a very important moment in science history to be sure there are other systems of planets out there. In our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets orbiting each one. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they've found more than 400. Some are huge spinning balls of gas that are 5 times as big as Jupiter. Others are huge rocky worlds many times larger than Earth. Some follow wild, irregular orbits so close to a star they're burning up. One thing is certain, no 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. In the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some formed close to the sun where it was much hotter, and some formed far away where it was much colder. Since the situations were so different, the things that came out of them were also different. At the beginning of the solar system, there was a pretty even mix of rocks, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. You'd mix the ingredients just like with a cake, then put it in the oven and bake it, and it would change. Basically, this is what happened in the solar system. The planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it's hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to solidify, and these very small mineral grains can begin to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust particle and another dust particle, they would basically hit each other and make one slightly bigger dust particle. They keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things toward it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were many young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid Vesta, you can get a good idea of how big a rocky planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then it has enough gravity to crush itself into a sphere. Any smaller and it stays in an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets, turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the baby planets started to grow at the expense of others. The things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller baby planets around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they're all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So it could have been a bigger planet in the past. Then something hit it at an angle which tore off the lighter crust and left only the dense center. Earth was also hit hard. At the end of Earth's development, it was hit by something else that tore apart its mantle and sent the pieces into orbit around Earth, where they regrouped to form the Moon. Something also seems to have crashed into Mars. The crust of Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust. That crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal-rich, those chunks would tend to fall down into what was becoming the core. If you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials, but each of them was very different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. That flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye. You see one of these every few minutes. Solar wind could kill astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we're protected by an invisible magnetic field that comes from the center of Earth. You can make magnetic fields from motion by converting the energy of motion into magnetic energy. Deep inside Earth, the same thing happens. As Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. Keeps the solar wind from getting into the planet's atmosphere. If the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes disturb the magnetic field. Then big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that's dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry with not much going on. So why have the two planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the Martian surface. They proved that Mars is a dry, dangerous desert with only 1% of Earth's atmosphere. But they did find signs that water used to be there. Mars wasn't always a dry, empty place. We found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that form when water flows over sand. So not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. Because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field, probably caused in the same way as on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. That means a liquid core can become solid. When it freezes completely, if you freeze the core, the flow will stop. The flow stops and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets Mars, Earth, Venus, and Mercury all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, and Neptune. All have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. We think we were able to make ice snowflakes, and these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big, because there was so much ice and gas. Their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled toward the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they're very weak and hard to find. But they're there. There are rings around all 4 gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they're made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some turn into small moons. Some fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They're so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they're in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside. Far below the storms, NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. On December 7, 1995, Galileo sent a probe into Jupiter's atmosphere at a speed of 160,000 miles per hour. As it fell through the thick air, parachutes slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe sent data back to Earth for 58 minutes. What happened to the Galileo probe we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up as it fell. It measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. Eventually, you would be crushed by the weight of the material above, even though the probe only went 124 miles down before it was crushed. It showed scientists what Jupiter's inside looked like, but the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have magnetic fields too. Jupiter's magnetic field is 20,000 times stronger than Earth's and so big that it reaches all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected Jupiter's moons. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. This makes the area around Jupiter very busy in many ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that gas planets also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They are the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they're fixed and don't change, but they're always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of Earth is water. Some water is on the surface as oceans, and some is stuck in the metal. But actually, Earth is a relatively dry rock. All the inner rocky planets formed very close to the sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit them. These massive collisions that formed Earth were so powerful that if there had been water here, it would have evaporated and left Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see they have a lot of water locked up inside them. Even more dramatically are the moons. At least half of the moons of Jupiter, Saturn, Uranus, and Neptune have water. A lot of water was out there. So how did some of it get to planet Earth? The answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of Earth. Without surface water, there would have been no life. What about too much water? The oceans would be much deeper and cover the continents and even Mount Everest. It's likely that the exact amount of water that Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There's a lot of water out there. That much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what's happening in our universe. So water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that's about the same size, mass, and chemical makeup as Earth. So it remains an extraordinary holy grail for humanity to find other homes that remind us of our own. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We're entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place with the right amount of water. One thing is certain. There are billions of planets out there waiting to be discovered. Our solar system is a harsh environment. Volcanoes are destructive everywhere, from the ice volcanoes of Saturn's moon Enceladus to the immense lava fields of Jupiter's moon Io to our own planet Earth. It's truly true that we wouldn't be here if there were no volcanoes. Volcanoes influence and change our climate. Volcanoes are both the creators and destroyers of life. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most powerful natural events on Earth. They create new land and destroy the old. They release gases that change the atmosphere we breathe. Deep in our oceans, Volcanic heat fuels strange new forms of life. Volcanoes help sustain life on Earth. Now we look for signs of life on other planets. We understand that life requires water. We know it requires energy, and this is where volcanoes come in, as they create huge amounts of energy. If we find volcanoes on other planets, we may discover life. The search begins with this planet that orbits Earth most closely, Venus, a planet that closely resembles our own. Venus and Earth have similar masses. Earth and Venus were very similar 3 billion years ago, with new land, new oceans, and an atmosphere. Both planets were favorable to life. On Venus, however, something went wrong. Something caused the history of Venus to split drastically from that of Earth. Venus took a definite turn to the dark side a long time ago. Venus is Hell, our evil twin planet. Today, the surface of Venus is like a furnace. The surface is 900 degrees Fahrenheit hot, actually heated enough to melt some metals. So you have no chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide. It absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot wasteland. The planet was destroyed by its dense CO2 atmosphere. The CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar broke through Venus's thick clouds and showed volcanic formations all over the planet. These formations look a lot like the shield volcanoes on Earth, round and flat. Shield volcanoes get their name from their shape. These volcanoes ooze, but they ooze for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discover that many were quite familiar. In particular, we saw enormous shield volcanoes that looked like the shield volcanoes in Hawaii. The radar images of Venus were identical to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were amazed to see a picture of Venus for the first time. We discovered a cratered volcanic surface. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life. Instead, it was consumed by flames. Many trillions of tons of carbon dioxide were expelled by Venus's volcanoes into the planet's atmosphere. The temperature rose dramatically. The oceans evaporated. On Earth, carbon dioxide is able to be absorbed into the rocks, can be absorbed by the ocean. On Venus, however, there's no water, and the temperature is so high that carbon dioxide can't even combine with the minerals. Volcanoes released carbon dioxide into the atmosphere ages ago, and as time passed, fewer and fewer methods existed to remove it from the atmosphere. Volcanoes sterilized the entire planet. If Venus ever supported life, it's long gone now. Earth is the only known planet with life. That may change. This is the gas giant Jupiter with its moons, believed to be frozen and lifeless. A mystery surfaces as a cloud hovering over a cold and lifeless world. Upon closer inspection, on Venus, volcanoes transformed a planet similar to Earth into a superheated hell. Volcanoes on a planet similar to Earth weren't a surprise, but the discovery of volcanoes on a moon was an astonishment. In March 1979, the Voyager 1 spacecraft provided us with our first up-close look at Jupiter's tiny moon Io, a world we once believed to be frozen and lifeless. And they witnessed something amazing. They saw this arc next to the moon, and it almost appeared as though there was a second moon behind it. We scratched our heads and asked, what could that be? Everyone knows Io is lifeless, dull, and uninteresting. And then people realized, oh my God, It's a volcanic eruption. We discovered that the area is covered in volcanoes. It's geologically extremely active. There are constant volcanic eruptions, and what they're erupting is a great deal of sulfur, which becomes extremely heated. Sulfur changes color as its temperature changes. It may be red, orange, yellow, or even black. As a result, these images of Io's face look like a pizza with different types of cheese and olives. Where the small black spots are, Io is not dead. It's alive and growing. There are more than 400 active volcanoes. The largest, Pele, erupts from a gigantic lava lake. It extends about 400 kilometers into space. It would be an extraordinary sight if we could stand on the edge of that lava lake and watch that plume shooting off into the void of space. Pele's eruptions are so massive due to Io's tiny size. There's nothing holding the lava back, as there's virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes look like fireworks. How can a moon so small be so volcanic? The answer is Jupiter. Similar to how the moon raises tides in Earth's oceans, Jupiter raises solid rock tides on Io. Io's orbit around Jupiter is not circular. Sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io. Jupiter's gravity stretches and squeezes Io in every 2-day orbit. The ground rises and falls by nearly 300 feet. This pounding creates extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism is therefore planet-scale, in contrast to Earth, where certain parts are active around the plates or in weak areas. This is an entire moon that's one active hotspot. Io is the most volcanically active place in the solar system as a result of the immense power of gravity. Volcanic activity on Io has taught us something new. It taught us that internal energy sources can drive volcanism in a manner different from that on Earth. Io is a lava world that's extremely hot and violent. It's difficult to imagine anything surviving there. We've discovered strange eruptions on many planets and moons, but so far, the only world where volcanoes are linked to life is ours. Or so we thought. This is Europa. It orbits Jupiter at a distance of nearly 500 million miles from the Sun and is a 2,000-mile wide sphere of ice. From afar, its surface appears to be polished. Up close, it's a different story. Europa is pounded by Jupiter's immense gravity, just like its companion Io. The surface rises and bends, forming ridges and deep cracks. When we first got close-up images of Jupiter's moon Europa, they seemed vaguely familiar. Turns out they look like Arctic ice flows. And it turns out they are the same. A global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements show Europa's ocean is an astounding 60 miles deep. The gravitational impact of Jupiter heats the rocky interior and melts the ice above. As the core is stretched by tides and heated, possibly melting, it's not crazy to think there's a boundary between a hot core and a liquid water ocean. Underwater eruptions on Earth are surrounded by life. The same may happen on Europa. Here, the darkness is complete. The pressure is a crushing 2,000 Earth atmospheres. A harsh environment, but perhaps a cradle for life. If there's evidence of life on Earth, why not Europa? An energy source, volcanic activity, a universal solvent, liquid water, and a complex hydrocarbon chemistry are all present. Life would be difficult but not impossible on Europa. There's life at every extreme on Earth, including searing heat, crushing pressure, and absolute darkness. Life on Europa may resemble our own in unexpected ways. If life exists beneath Europa's ice, it would be aquatic but without eyes because there's no significant light. Organisms that essentially feed off the energy of the volcano would most likely use sonar to make sense of their surroundings. Volcanoes on Europa could be the beginning of new life. It's even possible that Europa is typical, that this is the norm for planets with life. Earth may represent an exception. Consider that Europa could serve as a model for the billions of moons in the universe with liquid oceans. So all of a sudden, our horizons have expanded several billion times by looking at the moons of Jupiter. Our solar system is home to more than 170 moons. Multiply this by the size of the universe, and that's a lot of potential homes for life. Only liquid water and a source of energy are required. Potentially, both are provided by volcanoes, and they're everywhere. This is Saturn twice as far from the Sun as Jupiter. However, it also has volcanic moons, and similar to Europa, these moons could support life. Saturn is one of the odd planets in our solar system, with a 600,000-mile wide ring system and an astounding 62 moons. And one has a secret. Enceladus is one of the smaller and more distant moons of Saturn. It's been known for a long time that it's covered in ice due to its extremely bright and reflective surface. However, when the Cassini spacecraft visited the planet, it made a remarkable discovery. Not on the planet itself, but on Enceladus. The Cassini probe revealed a remarkable discovery: a massive plume backlit by the sun and erupting into space. This is clear evidence of volcanic activity. Cassini's sensors zoom in on the south pole of the moon to capture these enormous craters scarring its surface. At the south pole of Enceladus, there are extraordinarily large cracks that open and close as Enceladus orbits Saturn because of the tides. Now these cracks are enormous. They extend for hundreds of kilometers. When they begin to open, you would see a large crack opening at about 100 miles per hour along its length. It'd be incredibly amazing. Huge gravitational forces cause the surface to open and contract with incredible speed. This helps produce the heat necessary to melt ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It's at the perfect temperature. It would be good for life. Liquid water would be just like seawater here on Earth. The chemistry of the water we see erupting from these cracks suggests it contains salt. Contains organic matter as well. Therefore, we've identified a location in the solar system where there's a strong possibility that life exists right now. In the ice particles, Cassini has detected complex carbon molecules. In combination with liquid water, they suggest that perhaps life could exist deep within this mysterious moon. Enceladus is possibly not alone. Another of Saturn's moons might also harbor life: Titan. Titan is one of the largest moons in our solar system, the only moon with a thick atmosphere. A frozen world ice as hard as rock, lakes of liquid methane. Yet we may also discover evidence of volcanoes and the tantalizing possibility of alien life on this planet. Volcanoes are one of the most destructive forces in the universe, as shown by Io's raging fire and Triton's ice and nitrogen explosions. Even on Saturn's mysterious moon Titan, however, destruction can lead to the possibility of life. It has a diameter of 3,000 miles, making it larger than Mercury. It has the thickest atmosphere of any moon in our solar system. There's weather including storms, winds, rain, and even lakes. But the temperature is so low that liquid methane replaces water. It's loaded with essential compounds for life. Titan has proven to be one of the most fascinating places in the solar system. It's an active world. It's the only moon with a dense atmosphere, an atmosphere very similar to that of Earth because of the presence of nitrogen and, as it turns out, organic molecules. High in Titan's atmosphere, Methane gas reacts with sunlight to produce compounds essential to life. But if sunlight consistently converts methane into organic compounds, why doesn't methane run out? Methane is abundant in the atmosphere, but we know it's quickly eliminated by sunlight, so it shouldn't be there. There must exist a source of methane. Something on Titan releases methane in a continuous stream. Cassini has spotted what appears to be a crater. Infrared cameras reveal that the crater is surrounded by various types of materials. Scientists think the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid released by volcanoes could be either ammonia or water. Methane and ethane are released by Titan's volcanoes, and this is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely came from the outgassing of Titan's volcanoes. Even on a globe as rigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity massages the moon. Similar to Enceladus, these two forces produce enough heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive here? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide everything on Titan. If life does exist on Titan, it would be truly alien. It would breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane. Possibly there are tidal pools as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's speculation, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We may discover it on Mars, a volcanism-rich world much closer to home. Volcanoes are everywhere throughout the solar system. Planets such as Io, Titan, and Triton are complex, volatile, and violent. Once we believed Earth was the only planet with both volcanoes and life. Now we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes show the absolute force of creation and destruction. They go hand in hand. It's literally true that if there weren't volcanoes here, we wouldn't be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, and replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times when the solar system was young, on a planet similar to our own. This is the planet Mars. 3 billion years ago, volcanoes were active. The greatest volcano in the solar system still stands. The cliffs leading up to it are greater than 6 miles in height. Even Mount Everest would be comfortable in their shadow. This is the mighty Olympus Mons. Covers an area the size of Arizona. This crater alone is 53 miles wide. A structure of this size takes millions of years to build, a period of time that volcanoes on Earth never have. Earth's crust is constantly in motion. In the depths of Earth, a single hotspot forces magma to the surface, creating a new volcanic island. While the hotspot remains stationary, the surface is in motion. The new island moves away from the hot location and is replaced by a new volcanic island. Mars is different. The crust is locked solid. On Mars, there's simply no tectonic activity. The crust is one big solid plate. So if there's a hot spot, it just sits there and builds and builds and builds, and you get a bigger and bigger and bigger volcano. Therefore, Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era, an extinct volcano on a fading planet, now a true giant due to Mars's reduced atmosphere. However, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes on Hawaii have formed mysterious tunnels known as lava tubes, which form when rivers of molten rock rush into the ocean. Lava tunnels form when there's an underground river of basaltic lava, magma, and molten rock at 2000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface. It's the same, except here the crust is solid rock, and the river continues to flow beneath, creating this cave, this lava conduit. Recent images suggest that Mars's volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This life will be our own. Radiation will be one of the challenges that future humans will face when attempting to live on Mars, especially during solar storms. The incoming cosmic rays can be lethal. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, holding air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new life. Volcanoes are capable of both destruction and creation. The universe is a vast and mysterious place, filled with countless wonders and secrets waiting to be discovered. Among the many mysteries of space, one of the most fascinating and profound is the age of the universe itself. Scientists have spent decades studying the universe using a variety of tools and techniques to uncover the mysteries of our cosmic past. Through their efforts, they've determined that the universe is estimated to be around 13.8 billion years old. The search for the age of the universe began in the early 20th century when astronomers first realized our universe was expanding. The concept of an expanding universe was first proposed by Belgian astronomer Georges Lemaitre in 1927, but it wasn't until the work of American astronomer Edwin Hubble in the 1920s and 1930s that the idea was widely accepted. Hubble's groundbreaking observations of distant galaxies revealed they were moving away from us at great speeds, and the farther away a galaxy was, the faster it was moving. This relationship, known as Hubble's law, suggested the universe was not static but was instead expanding. If the universe was expanding, then it must have been smaller in the past, and this realization led scientists to wonder just how old the universe was. The first attempts to estimate the age of the universe were based on models of how stars evolve. Scientists knew stars undergo a predictable sequence of changes as they age, and they thought that by studying the properties of stars in our own galaxy, they could determine the age of the universe. However, these early estimates were plagued by uncertainties in our understanding of how stars evolve, and they varied widely from a few million years to several billion years. It wasn't until the 1960s that a more accurate method for determining the age of the universe was discovered. In 1964, two astronomers named Arno Penzias and Robert Wilson discovered a faint background radiation that was present in all directions of the sky. This radiation, known as the cosmic microwave background, CMB, is thought to be the leftover radiation from the Big Bang, the event that marked the birth of the universe. The discovery of the CMB was a major breakthrough in our understanding of the universe, and it provided scientists with a powerful tool for estimating the age of the universe. By studying the properties of the CMB, scientists could figure out important details about the early universe, such as its temperature and makeup. This information, in turn, could be used to estimate the age of the universe. Over the next few decades, scientists refined their measurements of the CMB and improved their understanding of the early universe. They also developed more advanced models of cosmic evolution, which took into account the effects of dark matter and dark energy, two mysterious substances that make up the majority of the universe. By combining these observations and models, scientists arrived at an estimate for the age of the universe, 13.8 billion years. This estimate has been confirmed by a variety of independent measurements, including observations of distant supernovae and the large-scale structure of the universe. The age of the universe is one of the most well-established facts in space science, and it has profound implications for our understanding of the universe. The age of the universe tells us our universe has a long and fascinating history, stretching back billions of years to a time when the universe was just a tiny, hot, and dense point. It tells us the stars and galaxies we see today are the result of billions of years of cosmic evolution, driven by the forces of gravity and the interplay between matter and energy. 13.8 billion years old, why is it still expanding at a speeding up rate? What is the nature of dark matter and dark energy, and how do they shape the evolution of the universe? How did the first stars and galaxies form, and what was the nature of the universe in its earliest moments? These are just a few of the many questions that space scientists are working to answer. The age of the universe provides a crucial piece of information in the quest to understand space, but it's just one piece of a much larger puzzle. One of the most fascinating aspects of the age of the universe is how it connects to the basic nature of space and time. According to Einstein's theory of general relativity, space and time are intertwined, forming a four-dimensional fabric known as spacetime. This fabric can be warped and distorted by the presence of matter and energy, leading to phenomena like gravitational waves and black holes. The age of the universe tells us spacetime has been evolving for billions of years, stretching and warping in response to the forces of space. It tells us the very fabric of the universe has a history, and the structures we see today are the result of a complex interplay between spacetime, matter, and energy. While the universe is expanding at a speeding up rate today, it's still unclear what the ultimate fate of the universe will be. Some theories suggest the universe will continue to expand forever, eventually becoming a cold and dark place empty of stars and galaxies. Other theories suggest the universe will eventually collapse in on itself, leading to another Big Bang and the birth of a new universe. Whatever the ultimate fate of the universe may be, the age of the universe tells us we're living in a remarkable moment in cosmic history. We have the opportunity to study the universe at a time when it's still evolving and changing, when stars are still being born and galaxies are still colliding and merging. By studying the universe and its evolution, we can gain insights into the basic nature of space and our place within it. The age of the universe also gives us insights into the likelihood of smart civilizations existing elsewhere in space. If life is a relatively common occurrence in the universe, and if the conditions for the development of smart life are present on other planets, then there may be many civilizations out there that are much older and more advanced than our own. Moreover, the age of the universe has implications for our search for alien life. By studying the conditions that led to the emergence of life on Earth and by exploring the diversity of life forms on our planet, we can gain insights into the types of environments and conditions that might be favorable to the emergence of life elsewhere in the universe. Some theories suggest the universe is just one of many in a multiverse, a vast and complex network of parallel universes with their own unique properties and histories. The age of the universe tells us that if a multiverse does exist, then there's been plenty of time for the emergence of many different universes, each with its own unique history and destiny. Finally, the age of the universe reminds us of the incredible beauty and wonder of space. From the cosmic microwave background radiation left over from the Big Bang to the complex dance of stars and galaxies across the night sky, the universe is a rich and complex tapestry of phenomena that's both awe-inspiring and humbling. In conclusion, the age of the universe is a remarkable fact that has profound implications for our understanding of space and our place within it. It tells us about the origins and evolution of the universe, the potential for alien life, the nature of reality itself, and the beauty and wonder of space. As we continue to explore the mysteries of the universe, the age of the universe will remain a key piece of information guiding us in our quest to understand space and our place within it.